how to work out y is equal to mx plus c. That is, you rearrange your equations so that you know which part is the y, where is the m, where the x, and where is the c, which is the intercept. Okay, so we'll move to the first question, which is June 20, paper 51. Okay, so this is June 20, paper 51. Now, let's look at this question. While reading this question, you will most definitely find something that you have not seen. But this will be your, what we call it, like first impression. Okay, but if you read the question properly, okay, you will see that it is linked to a topic somewhere which you have done. So just, oh, it's already here. All right, so trichloromethane, which is trichloromethane, which is CHCl, a halogenoalkane. If you look at your notes on shapes, just one sec, there's more students who are coming. So if you will look at your notes from shapes, you will find out that it is a tetrahedral one. This is why it has been drawn tetrahedral in 3 dimensions. Okay, and if you continue looking at your notes where you have the intermolecular forces, you will find out that we have done this molecule and that all the Cls, they pull the electrons downwards. That is why I put the delta minus here. And then the upper part, which is the H, it becomes delta plus. So this trichloromethane is a polar molecule. And propanol, now you're used to propanol. So many times you have seen it in paper 2. So you have the CO, which is again polar. The CH3 is non-polar, but the CO is polar because the oxygen is more electronegative. So the oxygen gets a delta minus, and this delta plus is for this carbon CH3 over here. We can say that this CH3 part is non-polar. Okay. Now the molecules within each liquid are attracted to each other by relatively weak permanent dipole interaction. So if you have CHCl3 and CHCl3, so if I just write it down like that, CHCl3 now another CHCl3. Here I have weak permanent dipole forces of attraction. And again, if I put it over here, if I have CH3, CO, CH3, again same, we have the weak permanent dipole forces of attraction. This is present within the molecules. Now, what is happening? We are mixing trichloromethane with propanol. So when we are mixing trichloromethane with propanol, what we have to understand is that, I just try to put it over here, say the weak permanent dipole forces are broken, and new force of attraction formed. So the permanent dipole between the chloromethane over here, it breaks. The permanent dipole between the propanon, it breaks. And what is formed is a new electrostatic force of attraction. If you look at this new electrostatic force of attraction, you will see that it is a hydrogen bond. And we all know that hydrogen bonds are strong bonds. Okay, so here, here we have hydrogen force which is formed is hydrogen bond. We all know that hydrogen bonds are stronger forces of attraction. So we have bond breaking which is taking place, which is endothermic as heat energy is absorbed, and also we have bond formation which is exothermic as heat energy is released. Okay, here. So we have the breaking of the weak permanent dipole forces of attraction. And we have the formation of stronger hydrogen bonds. So when the weaker bonds are broken, it is endothermic, and the new stronger hydrogen bond which is formed, it is exothermic. Now, a student plans to perform an experiment to investigate the strength of this electrostatic attraction by finding the temperature change when equal volumes of trichloromethane and propanon are mixed together. Now, if the bonds which are broken were stronger than the bonds which are formed, then overall it would have been endothermic. Okay, so please just write it down somewhere because I don't have much space to write this down here. Just for some place. Okay. Just write it down. So you write down prediction temperature decreases. Write down like it is here. Prediction temperature decreases, and you write down if the bond broken was stronger than the bond formed, then more energy would have been absorbed. I repeat again, if the bond broken would have been stronger than the bond formed, then more energy would have been absorbed than released. Okay, so here, this knowledge we have to use to get this A part 1. Okay, so we are breaking weak intermolecular forces, which are permanent dipole forces of attraction. We are forming another weak force. Hydrogen bond is a weak force, but hydrogen bond is stronger than permanent dipole forces of attraction. So when we are forming a stronger bond, more energy is being released than absorbed. So this is how you get the first part. Okay. Now the student is given only the following equipment and chemicals for the experiment. So whenever you see these chemicals, okay, we see thermometer, measuring cylinder, beaker, okay, you will know that we are talking about the calorimetry. Okay, the calorimetry is where you have the polystyrene cup, okay, and the thermometer, and you are adding the solutions. But over here, you will see that we do not have a polystyrene cup. We are using a beaker. So this may be a mistake in doing the experiment, where we could better the experiment by using a polystyrene cup, which will be held in a glass beaker. But we will see if we are asked that question afterwards. So we are given a 25 centimeter cube beaker. Of course, we cannot use all the 50 centimeter cube. We have to use less than 25 centimeter cube. So I'm using 10 centimeter cube of each, which comes to a total of 20 centimeter cube, and there won't be any spilling. What I have to take, we all know that we have to take the initial temperatures of both liquids. Okay, so what we do, we just place them in the measuring cylinders and we insert the thermometers. I think we just did an experiment like that before the lockdown. Okay, leave to equilibrate is we just do not dip the thermometer, and we say that we have got the answer that we want. We have to leave it for some time, just like we do in practicals. And then what we do, method use, we mix the two liquids in the beaker, then we monitor the temperature every minute until temperature falls, starts to fall or reach the maximum temperature. So I have attached a attachment over here. We see June 2004, question number 5. Okay, just one sec. It is not the same question, but over here it is about zinc and copper to sulfate. Okay. In fact, I should have attached also the examiner's report. I forgot about that, so I will attach it afterwards. Okay, so here this will be your table. Why I've attached this? This is your table that you should have done. Okay, so in exams, if you are asked the table, this is the table that you should have produced for this question, and the graph would be temperature against time. Okay, so this attachment is already here. Just give me 1 minute. And your graph would be like this. Okay, I hope that you can see the graph. You are used to this graph where the first temperatures are horizontal. Okay, there's no change, and then after you have added, then there is a sharp increase and then it decreases, because we all know that an exothermic reaction first gives us an increase in temperature and then it gives us a decrease in temperature. In fact, an exothermic reaction, this is the exothermic part and this is the endothermic part, the decrease in temperature. An endothermic reaction, it has got the endothermic and the exothermic. Please check your notes of enthalpy changes. You have the graphs where you see that it increases to a maximum and then it comes back to normal, or it decreases to a minimum and then it increases to a maximum, to the normal. So in an exo you have exo and endo, and in an endo you have endo and exo. Okay, so you will see that the question started like with trichloromethane or propanone. You may have thought that you have not done anything, and then you panic, and then you start working it wrongly. Read the question from the first till the last part. Okay, you just have to read the question from the first to the last part, and then you will see that it is an easy one. Okay, so we just continue. So you have heat loss, so you know what you have to do over here. Heat loss. One relevant precaution: I think in this experiment only, this practical only, for this paper. Okay, the questions were, the answers in the marking scheme were a bit different, but I've chosen the best that I found is not to perform a naked flame, because I don't see why we should have a flame next to this experiment, because we are not being told to do other experiments. So the marking scheme, there is something different being written also together with this explanation, I think so. So I've chosen the best of them. We all know that the values that uh, found out what are measured using measuring cylinders are not that accurate, so it's better to use a burette or a graduated pipette. Of course, it is not a pipette, it is not the normal pipette, it is a graduated pipette, okay? Or even if we are using a pipette, we have to say that we are going to use a what we call that, a pump, a safety pump, as we cannot pipette with the mouth organic liquids. Oh, we use larger volumes. I hope that you understand why we use larger volumes. Larger volumes gives us larger changes in temperature. And when we get larger changes in temperature, it gives us lower gives us lower percentage error. We all know that percentage error is inversely proportional to reading. The larger the reading, okay, the larger the reading, the lower is the percentage error. We use a more accurate thermometer. We are being told over here, we have not been given the thermometer uh, uncertainty, so we cannot talk about 1 degree Celsius thermometer or 0.5. So it's better just to write down, use a larger thermometer. I hope the number of moles is okay, the delta H is okay, all right? Suggest an experiment, the student, where the number affects the temperature change. So here, trichloromethane becomes the independent variable. So what we have to do, propanone will be the control variable. Temperature change will be, of course, the dependent variable. So like I told you, the question in the beginning looked to be difficult, but then it was not that difficult. It was quite easy to score the 11 marks. Okay. We come to the second question. Okay, where nitrogen dioxide is being prepared by heating anhydrous lead nitrate. Yes, just coming to the anhydrous lead nitrate, thinking about the experiment. Okay, lead nitrate you won't be given in the exams if you have to heat, but you can be given zinc nitrate, which is a white solid, which it gives you a yellow solid when hot, and which becomes cold. When it becomes cold, it becomes white. So in that question, if you have to heat the solid, you will be told to leave your residue to cool. So when you will be told to leave your residue to cool, so it will mean that you need to let it cool down and then observe the color of the residue after cooling. Most of the time, it is from yellow to white. And you will know that you have a nitrate because you will find brown fumes coming, and as soon as the brown fumes are coming, If you take a glowing splint, it will relight a glowing splint. Also, I've seen that there are 2 batches of practicals for this year. Okay? We have 2 batches of practicals, one on the 18th of May and one, I think, on the 1st of June. So those who are giving exam, that is the HSC group, please send me your dates in your confirmed timetable if you are giving the first batch or the second batch. Even for physics, it is like that. And Cambridge has made a mistake in sending information to CIE. So we have 2 batches, okay? So you just forward me on which date you will be giving the exams. Now, draw a label diagram, prepare liquid nitrogen dioxide from the thermal decomposition of anhydrous lead nitrate. So we have to heat the tube which contains lead nitrate. And then the nitrogen dioxide, you can see the melting point in Kelvin. Okay, this is the boiling point. So if you minus 2,9 273, I hope 273. So we get around 21 degrees Celsius. Okay, so we can use ice. So this is why we are using ice over here. And these are the labels. So the diagram which is accepted by Cambridge is something like this. Okay. So this is the diagram. You can see that the ice bath can come to a minimum of 0 degrees Celsius, okay, or -4, something like that. And we won't be reaching that temperature to cool the oxygen over here. So the oxygen will be collected in the gas syringe. Okay, so the nitrogen dioxide will be collected over here. Okay, so here I would like you to label this part as liquid nitrogen dioxide for just for your own sake. Okay, liquid nitrogen dioxide, here delivery tube, and here oxygen is collected. Okay, delivery tube, liquid nitrogen dioxide, and here oxygen gas, because oxygen is going to remain as oxygen gas. Only the nitrogen dioxide which is going to be converted into liquid. Okay, so just add those small ideas. They will be very helpful. At room temperature, so here nitrogen dioxide exists in equilibrium with dinitrogen tetroxide according to the equation shown. A bit of paper too. It is kilopascal. All right. Now, listen carefully to what I'm going to tell you, because at the end of the question, you have been asked all of these. And Cambridge has made it a bit difficult, but all the answers were found over here. Okay. The numerical value of Kp will depend if the overall reaction is exothermic or endothermic. Now, last time we all have looked at one part where I have been telling you that Kp, Kc, P, Pc, and K, SP values change with temperature. Okay, we also know that Kp is directly proportional duct partial pressure of product and inversely proportional partial pressure of reactant. So here, if you have the knowledge of Le Chatelier's principle and what I've just told you, okay, you will get the answers for the last part. No need to look at the graph. Okay, those who have worked out the question will understand what I'm talking about. So if this is delta H exothermic, okay, so an increase in temperature will give me brown and the value of Kp will decrease. If this is exothermic, a decrease in temperature will give me a higher Kp and colorless. So you just apply your Le Chatelier's principle with a change in temperature. Okay. So I'll just cancel it. So student plans to investigate the variation of Kp with temperature. So here, Kp is the independent variable. Uh, Temperature is the dependent variable. Oh, sorry. So temperature is the independent variable. I just made a mistake. So here, temperature. So temperature. So we are changing temperature is the independent variable. Kp is the dependent variable. Okay. So we have to ensure that when we are doing the experiment, the temperature is, when we are doing the experiment, let's say at 295 Kelvin, the temperature should remain 295 Kelvin. And how to ensure that? We use a thermostatically controlled water bath. Just 1 second, I've just come to part F. I'm just checking my phone. I saw that there is a question here. Key volume of propanol same and vary the volume. What is the number of moles? Yes, Angélicité, for your question, okay, yes, we can also vary, okay, the volume of trichloromethane, okay, and just keep that of propanon constant. Okay, it is going to be the same. Okay, so your answer is correct. Another. What is the problem with 51 E first part? Keshav, given what are the graphs? I don't understand why you're sending me these graphs right now. And E second part is simply uh, you're given energy release, so you are already given over here the value of Q. Okay, if this is the problem, question 1E second part, you're already given the value of Q, which is 1.67. All right, and you just have to divide it with the number of moles of any one of them, because not any one of them, of that with the limiting, because this is the limiting. Okay, reagent. In fact, we are finding delta H, and this is the excess reagent. Right. So usually what we do, we find Q, MC delta T, then the number of moles, and then delta H. But over here, we are already given Q, and we have found number of moles. Number of moles, they are different, so we take the limiting one, and then we just divide. And why the minus over here? Because we already know that the reaction is exothermic. So I hope that the issues for the first question have been solved. Okay, for these two parts. Now we go back to question number 2. I hope that the table is fine. Okay. Now we'll go to the graph. Give me 1 second, please. So when we go to the graph, seeing the graph right now. Here. Okay, so I hope that all of you are seeing the graph. So this should be the graph. Okay, you have some anomalous values. Okay, I don't know if you can see it properly, but we have some anomalous values. But what is important is that we have to take coordinates which are within the first and the last coordinate which are given. It should be large enough, occupy around 75% of the graph, so that you can do the gradient. Okay, so it will all going to depend on how you plot your graph. Okay, so you have some anomalous values. It does not pass through 0, 0 as it looks like. Okay, you have to use your what we call a ruler, so that it passes for the maximum number of points. So right now I can't tell you what are, if your graphs are correct, yes or no, but try to use your ruler, okay, to find out that it passes through the maximum. And come back to the marking scheme here. So when you get a best fit line, remember best fit line, it is can be a straight line or a curve. Okay, so here we have got a straight line, even if it does not pass for 0, 0. Okay, state and explain what your graph shows about the accuracy. Okay, like I've written down a note over here which will be sent to you, that the accuracy from graph is obtained by looking at the percentage of coordinates which lie on the best fit line. We need to have most of the coordinates lying on the best fit line. Here we saw that many did not, so it is not that accurate. Okay, maybe temperature is difficult to record. This is what Cambridge had asked. Okay, because what we are doing, we are investigating the variation of Kp with temperature. Okay, so if we are not heating, we are using a water bath, sometimes they may have some fluctuations. How to improve the accuracy? Remember your titration. Always remember your titration. Okay, so your accuracy is to repeat and take an average. You need to have concordant values, so we need to have concordant values. Get used to these words, because these words are important words. Concordant values. Now for the coordinates, like I said, take two coordinates which are in between the first and last coordinates, and it should cover the 75% of the line you get. You get your gradient. Like I told you over here, you need to be used to the fact of y is equal to mx plus c, which is going to help you to calculate the delta h. All right. When you calculate the delta h, here, because when you calculate the delta h, you will see that your delta h becomes negative. Okay, right? It becomes negative over here, right? So now when you get this delta h to be negative, then Cambridge is using this part, okay, is using this part for you to answer F part 1 and F part 2. But, okay, all right. If you look at this table itself, when we have an increase in temperature, we have a decrease in Kp. Okay, when we have an increase in temperature, we have a decrease in Kp. So if we have an increase in temperature and a decrease in Kp, it already shows to us that the delta H has to be negative. So, because why is that so? It is because when temperature is increasing, Kp is decreasing, okay? Temperature is increasing, Kp is decreasing. It means that we are going more towards the product, because for us, we have to go towards the product for, not towards the product, sorry, towards the reactant. Okay, we are going more towards the reactant, because when we have more reactant, our Kp decreases. This is why this part is very important. You please read it again and again. This is the method that this question could have been answered without even getting these answer delta H correctly. So these 4 marks over here were not related to the delta H. If you thought it was related to the delta H, I hope that now, after seeing the table, after seeing the link between the table and what I have just said, okay, you will find that it was easy to get the marks, these 4 marks, even if the delta H was not correct. Okay, so this is about the paper 51. Okay, we'll just take a small break of 5 minutes. Okay, don't log off. Okay, just remain logged in. Okay, we'll just take a small break of 5 minutes, and then we are going to look at the second paper 52. And I'm going to send you the marking schemes after our session. uh, you can then have a look at them. Okay, so just take a small break of, let's say, 7 minutes. 7:20 we rejoin. Okay, so let's start with the second one. So this is the second question. Okay, we go a bit fast for the first question because it was quite simple. Over here, the word soluble was already present in the theory over here. So, sorry, method A is not proper, it has to be method B. Okay, if you are asked about it, okay. So, because it is soluble, this is the first reason. And remember, second reason, when you heat, there is expansion. When you cool, there's contraction. So if you do not remove this delivery tube from the inverted measuring cylinder, there'll be water sucked back, and this container over here is going to break. Okay, this vessel over here is going to break. Okay, now you're being told why the first volumes which are coming out cannot be used for the MR determination of gas X. So we have just to remember one thing. This delivery tube, this flask, the flask, the delivery tube, they are all full of air, and air will be a contaminant in this experiment. Okay? Air will be a contaminant in this experiment. So we have to neglect the first parts, okay, the first few volumes which are coming. We have just to neglect them. How we are going to do that, Cambridge has not asked, so we are not going to bother about it for the time being. But this is what is written. Okay, then I have written down that every tube is full of air. Remember, only vacuum is empty. So that air is going to be collected all also. Next, soda lime. Okay, they have already given us some data about the soda lime, sodium hydroxide and calcium hydroxide. So these are chemicals which are basic, so they are going to absorb the acidic gas. Now, so the acidic gas which has been collected over here, right? Because we are using copper turnings, so we'll get nitrogen dioxide, most probably. Okay, usually it should have been concentrated nitric acid. I don't know why they have used sulfuric acid, but it works also with sulfuric acid. But usually it is concentrated nitric acid because concentrated nitric acid is both a strong acid and a strong oxidizing agent, and you get a salt plus water plus nitrogen dioxide. So, like over here, we cannot take the total volume. So, just write down something over here. We cannot use the total volume collected for further calculations. So you see, we do not remove the impurities. So what they have done, they've taken the gas syringe and then they've passed it through soda lime. So soda lime, what it is going to do, it is going to absorb the acidic gas, and the non-acidic gas, mostly air, is going to pass through unaffected. We may have a slight change due to carbon dioxide, because carbon dioxide also is a acidic gas, but it is only 0.003%. Okay, Cambridge has not taken that into consideration, but I'm just telling you that here the soda lime, it is going to not only absorb the acidic gas which has been produced from the earlier experiment, but also the carbon dioxide. But I think the volume of carbon dioxide, we all know the percentage of carbon dioxide is very, very minimal in air. So when it is minimal in air, it is not going to bring such a big change. Okay. Right, so let's continue. So what we are doing, we are measuring the mass before and the change in mass. So the change in mass will be equal to what we call the gas produced. Okay, so this is what we are looking for. This part I've already told you about. It is because soda lime is alkaline, so neutralization reaction will occur. Now, for respiratory distress, we all know that if we have what we call our toxic gases, we have to use a fume capote. Now here, I hope the calculation part was okay, because it was pretty direct. We just had to convert the temperature and the volume into temperature into Kelvin, volume into meter cube. The pressure was already Pascal. Okay. To determine the MR. So what we have to do over here now, so we have X, which is the mass. Okay, so when we divide the mass by the MR, so we have to find the MR. Okay, so divide mass of X by the number of moles calculated in D part 1. So this is usually what we usually do. So MR is equal to mass upon number of moles. Okay, so you just divide by the number of moles. Like I said over here, remember 1 mole of a substance is equal to its AROM. Or another student could have said 4.01 fois 10 puissance de moins 3 moles of X is equal to 0.25 n-gram. And then 1 mole of X is equal to 0.25 n divised by 4.01 fois 10 puissance de moins 3. Or you can use the formula for MR. Not all the gas of X is absorbed by the soda lime. So what effect? Okay. So here, if not all are absorbed, so the mass of gas which will be collected will be lesser. And again, you just look at over here, please, so you can see that MR is directly proportional to mass. That's why I've written this part also over here. So when MR is directly proportional to mass, okay, so when the mass is lesser, the MR will be lesser. For this part, I've added, there is a attachment over here. Please look at the attachment and see that if you have understood it, because it's mostly mathematical, it's becoming a bit difficult to explain it. So you will have the attachment, you please look at it and then revert back if you have any problem with it. Here we all know reliability is to repeat the experiment. Now if you have a gas which is alkaline, of course what you have to do, we have to absorb the alkaline gas using an acid. So you can see that it was pretty forward, except for this part for 1 mark. So out of 13, a good student was expected to get 12 out of 13 or 13 out of 13. Okay, because All the rest are things that you have done here and or there. Okay. Now we come to the second question. Again, this one. When you will look at it, you will find out that you've never done it. But you know, I was looking at a question in ATP, where over there, copper was being heated and or copper oxide was being heated. Sorry, copper oxide was being heated and hydrogen gas was being passed through it. And then there's a part in the question which says that why after heating is stopped, the hydrogen has to be passed for some more time. So the answer over there was very simple. It was because uh, hot copper reacts with oxygen. So you are reducing copper to oxide to copper. Okay, you are reducing copper to oxide to copper by passing hydrogen gas. Okay, and this reaction takes place upon heating. So if you stop heating and stop the hydrogen gas supply, of course, air will start passing through, and air is around 20% of oxygen. So your copper oxide will be again converted back to copper. Your copper will be converted back to copper to oxide. So please just have a look at that question. And again, over there in that question, you had a part where you had the excess hydrogen which was passing. We could not liberate it in the nature. So we had an ignited flame over here. That is, the hydrogen was burning, because we all know that hydrogen is flammable. So we could not let the hydrogen be left like that. It would have caused an explosion if there would have been naked flame around. Okay. So this question is more or less with this part, okay, is more or less related to what I've just been talking. So you see, you have iron wire. So you're passing chlorine through it, you're heating it until all has completely reacted. Allow the apparatus to cool while chlorine gas still flowing, because if we have any unreacted iron, it is going to react with oxygen, because we're allowing to cool. Remember, air is flowing. And then we weigh the sidearm conical flask containing the chloride of iron. So here, so in fact, we are going to see if the change in the mass. Okay, here we have the initial mass of Fe. Here we have the mass of FeCl. We call it as X. But we all know that X can be 2O. Okay, we all know that these are the two most common oxidation number. Okay. So of course we have to take the mass of the empty reaction tube, because we have to take the initial mass and the final mass. Then we will know the mass of Fe used, same as in practicals. You can make a table over here. Please make a table for this part and that part. So you have initial mass of, so you write down mass of empty reaction tube, then mass of reaction tube plus iron per gram, then mass of iron used, then mass of empty sidearm conical flask per gram, mass of sidearm conical flask plus FeX per gram, mass of FeClX formed per gram. Only one table with 1, 2, 3, 4, 5, 6 rows. You can see You can say the A, B, then you say C is equal to B minus A, then D, E, then F is equal to E minus D. Please make a table, right? Because you never know if you get a question where you have a table. So you already have a table over here. While revising, you will be ahead of other students. Just don't look at the marking scheme. Think ahead. This is what is called planning. Okay, here what we have to do, of course, we have to keep on saturating the apparatus. That is, we have to blow off any, instead of this word, so we say like evacuate. We have to evacuate any air slash oxygen remaining. You just say that only vacuum is empty, others contain air, so we just have to remove any air which is present. State an assumption that has to be made for the measurements made in this experiment to be valid. Okay, so I would have gone with all the iron wool has reacted. Okay, why? Because I'm ensuring that we are reacting all the iron. Somewhere it is written down here. You see, heat the iron wire until has completely reacted. So this is my first assumption. Okay, so all the iron wool has reacted. Okay, then secondly, the mass of air in the flask is equal to the mass of chlorine in the flask, because we have to assume that whatever was present in the beginning, just like in part 2, has been removed. So we have only chlorine. But for me, the best answer was all the iron wool has reacted, because I'm just going with what Cambridge has told me beforehand. These are the calculations. Okay, I hope that you have checked your calculations. Okay, your graph. This is the graph. Just one sec. In the graph, I think we have a few 102 which are anomalous. We have this one which is anomalous. The others are not anomalous. You can see that it is passing close to it. Okay, and it passes through 0, 0. Only one is anomalous. So when it is anomalous, we can see that the amount of chlorine atoms is less than expected. So here I would expect you to write down for yourself here anomalous value, amount of chlorine atoms used per mole is less than expected, because chlorine is in the y-axis. So when we move along the y-axis, we see that the amount of chlorine atoms that we needed was where my pointer is, but in fact it is lower. Okay, so it is good that sometimes you write it down. You put I don't know if the question is asked, we are going to see afterwards. You can just put also a construction line to see where is the expected value. Okay, because sometimes you may be asked that part also. So if you are asked about iron, then this is the expected value. So for iron, it is again an anomalous value, but for iron, it is that amount of iron per mole used is more than what is expected. Because when we go along the x-axis, we should have been on the left, but we are on the right. But if we go along the y-axis, we should have been above, but we are below. So please listen carefully. For iron, it is more than expected. For chlorine, it is less than expected. You put some dotted line, that is construction lines, and look for the expected values for it. So we have an anomalous value. Let us see if we are being asked. Yeah, we have an anomalous value. Okay. So you see, why the number of moles of chlorine is too small. So maybe not all the mass of iron chloride was collected in the conical flask, because uh, that's why I told you, make a table above. When you make a table above, you will see that the number of moles of chlorine is what? It is FeCl(x) minus Fe. Okay, so why we are getting moles of chlorine less? So maybe not all of them has reacted. Okay, so if not all of them has reacted, what has happened? So if not all of them has reacted, what has happened? Maybe some of the iron-free chloride, or iron chloride remain in the reaction tube. Okay, so you did not get it transferred to the conical flask. Or if it got transferred to the conical flask also, remember we have an outlet for excess chlorine. Maybe some of the iron-free chloride has escaped. Okay, then again you have in the coordinates, you just take your coordinates, you take your gradient, and I hope that all of you have been able to show how to get FeCl free. It was very easy. Okay, you just have to calculate the ratio of Fe to FeCl free. It is same as empirical formula. Okay, same as empirical formula. I hope that I'm showing the same thing. Okay, so you get FeCl free. Could have shown it in the exams. So you get the FeCl free. All of these are going to be sent to you, so then it will be easy for you to look at it. Percentage error, it is what we call as uncertainty divided by reading multiplied by 100%. I hope that you know that. Or it is 2 times uncertainty divided by reading multiplied by 100%. So here you will see that here we have a change in mass. So how we get change in mass? Change in mass is final minus initial. So when I'm taking the final, I'm having an error. I'm taking the initial, I'm having an error. That's why we have to multiply by 2. Now here we are given 2 decimal places. When we have 2 decimal places, our least count is 0.01 grams. So if our least count is 0.01 grams, our uncertainty is 0.005 grams. This is why this has been used, 0.005 grams. But you know, sometimes in marking scheme, you will see that for balances, if the student uses the uncertainty or the least count, Cambridge does not penalize. But unfortunately, so what I mean is, if a student uses 2 fois 0.005 ou bien 2 fois 0.001, he or she is not penalized. The student is not penalized. But for June 2020, because it was already confinement in UK, we do not have the examiner's report. So if we do not have the examiner's report, we are going just by what the marking scheme is saying over here. State whether the results from student 8 will have more or less percentage error than those from student 3. So we have to look at our table. So student 3 has used 1.14, here 3.90. mass of chloride also is 7.2. Say that percentage error is inversely proportional to, just write it down here, percentage error is inversely proportional reading. So when it is inversely proportional to reading, you can see from this formula over here. So if your reading is larger, your percentage error will be smaller. And last part, F and G over here, show that the formula is FeCl2. So again, either you could have shown it by the percentage, okay, by taking the mass of iron upon the MR multiplied by 100 for FeCl2, at 45, so it confirms that it is FeCl2, or by looking at the empirical formula, which was shown to you in this part, okay, here. So part D and part F, first part are the same. Explain using the electrode potential values why the method in A and F do not produce the same chlorides. Okay, so if you do the conversion, you are having Fe, okay, you're converting it to Fe2 plus. So if you reverse this equation, you will get plus 0.44, which is energetically feasible. But if you take the Fe2 plus and try to convert it to Fe2 plus, that is the Fe2 plus goes on the left hand side, here you will find that it is energetically not feasible. So you just had to reverse the equations and put them in the proper method, okay, to see if it is positive or negative, okay. Just have one thing to check over here. Okay, so this is the gradient. It is a bit blurred, okay, but this is what the student has used to for the coordinates for the gradient. You can see it is, I hope, yeah, this is the first and this is the last. So in between the first and the last, and it is big enough to uh, cover around, okay, 75%. So here, this is the dotted lines, okay. So you can see it is almost 75%, and it is between the first and this is the last coordinate. Okay, so we are done for today. Now for tomorrow, we had some papers. Okay, let me just check something. So for tomorrow, okay, Saturday, 9:30, paper 4. Okay, grade 13 students, please send me your queries because I did not get time to prepare the marking scheme for the paper 4 as I'm used to. Okay, even grade 12 students. So just send me your queries so that I can work it out. Instead of 9:30, let's meet at 10 so I get some time to prepare the paper 4. Okay. I've also forgotten which paper 4 was given. Okay, someone just just send a message in the group. Okay, someone from Saturday or Sunday upper or even Wednesday upper, just send me a message to let me know which paper 4 was given. Okay, so that we know what has to be prepared, and send me your queries. Okay, give me some time, so it will be at 10 o'clock because it's only tomorrow morning that I'm going to look at it now. grade 13 and grade 12 students who work all the questions, or even if you did not work all the questions, just send me your marks, okay? Let's hope that for grade 13 you are able to score above 20, okay? Let's put a range above 20. Even if you scored below 20, it's not a problem. We are going to work paper fives also now, okay? I will tell you the day and the time. We are going to meet almost every day next week. It will be 6 o'clock. So we will have paper five and paper four, paper five and paper four. Same as for paper two, where it was encouraging to see that most of grade 13 students were able to cross 50 marks. I hope that for paper two also, even if you're getting less than 20 marks, with time you are going to get more than 20 marks. This is the second thing. So first thing, you send me which paper I have for tomorrow, which paper for, okay? And then I will tell you which ones we are going to correct. But remember, you have to work all of them. Send me your queries. This is two. Third, send me your marks for the two paper files that we need to take. And fourth, uh, send me in the group itself for grade 13. Send me in the group itself on which date you are sitting for your practicals. Okay, you send me in the group itself the paper for tomorrow. The queries you send it to me private, grade 13 and grade 12. Your marks you send me private message, and exams, practical exam, you send it in the group. Okay, so we end up over here. If Kavish was able to record the session, please do the needful. Okay, we are thankful to you for all those recordings. Okay, so we end up today. I'm waiting for the latest details from you. Okay, so bye for today. For tonight, I must say. Okay, bye.
Otanis.